Okay, let's see. I did address some questions on the Jamboard, and so don't forget about that, because question number 1 on the gas stoichiometry is one that you'll want to take a look at. That's probably the most difficult one in the problem set. So you may want to work number 1 last on that one. Let's see, I just saw Will come in there. All right. Okay, so let me share screen. All right, so this one. Okay, let me make sure. Okay. Okay, so today we're basically looking at properties of mixtures of gases. And the key thing to remember is that it doesn't matter what the gas is. Okay, so our total pressure is going to be the pressure of all the gases hitting the walls of the container. So the frequency of those collisions. The key thing, we have a new term here that is, wait, I'm not on my drawing here. Okay. The key term that we want to, or a new term we want to address, is partial pressures. So the partial pressure is, that is the fraction of the pressure, of the total pressure, that's due to a single gas. So if I have a mixture of oxygen and nitrogen, the partial pressure of the oxygen would be the pressure that is just due to the oxygen molecules collisions with the wall of the container. So it's just going to be a fraction of the total, and it'll be, the fraction will be relative to the fraction of the molecules of oxygen to the molecules of the nitrogen in the mixture. Okay, so here we have basically that those pressures, those partial pressures, are completely additive. The fact that they're in a mixture doesn't reduce their effectiveness or anything like that. So the total pressure is just the sum of the partial pressures of all of the gases that are in the mixture. And we can, so like, for example, if we were doing like a PIV-NERT with the total pressure times the volume will be the same because they're all in the same container. And then our total moles would be the sum of all the moles in the container, then R, and then the T is the same for all of them because they're all at the same temperature. And then I can also PIV-NERT for any of the individual gases. So if I'm using, or if I want to find the partial pressure of a specific gas, then I would use I would solve for the pressure of that gas in the volume using only the molecules of that gas. Okay, so I can kind of break down the PIV-NERT using partial pressures as long as the moles is just the moles of that individual gas. A process that we do, hopefully we will get to do this in the spring in the lab, is when we generate a gas and say we want to use that gas for something. So collecting a gas over water is a really common, easy way to get a gas to use later. So this is just an example here. We've got potassium chlorate decomposing, and essentially this water bottle here, that would be completely filled and then inverted. And so the oxygen gas that's being generated is going to bubble up through here And so the oxygen would come in here, and then it's going to force the water out. Okay. Now, the thing is that because it's over water, you do have some water vapor that is in this space. So I'm going to write this bigger. So that vapor space there has oxygen and water vapor in there. So the pressure that's inside there is due to the oxygen molecules and the water molecules. So the way this works is that we would collect the gas, and then what we would do is take and lower the container that has the gas in it to where, okay, maybe I can draw this a little better. Usually we do this in a really deep tub, and the thing that we have, right, it has markings on it, kind of like a graduated cylinder does. All right. And so what we would do is we would raise or lower that tube so that the water level inside is the same as the water level outside. Okay. And so now let's think about it. If when I do that, right, I've got atmospheric pressure that is pressing down on the surface of the water, right? And so kind of think about our manometer that we talked about on the first day. So if I've got atmospheric pressure pressing down, if the pressure inside of that container is lower, right, then the water level is going to be up higher inside the container. If the pressure inside of the container is greater than the atmospheric pressure that's pushing on the water, then the water level inside is going to be lower than the water level outside. So what I do by lining it up to where the water level is even, it means that that atmospheric pressure and the pressure inside the container are the same. And so that's how I'm able to measure the pressure that's inside. So I would adjust this so that the water level's even, and I take a reading of the atmospheric pressure, and so then I know that the pressure inside, or what we are calling P total, is going to be equal to the atmospheric pressure. And then when it's even like that, that's when I take a reading of this volume. Okay. And so that will get me my volume that I read that. And then of course I can also take a reading of the temperature as well. So we measure that, we measure our volume. Okay, and then based on that, I can figure out the moles of the gas that's inside of the container. So I'll know how much did I collect. Now, the key thing is that I'm only interested in the gas that I was generating. So in this example, I really only care about the oxygen, but my pressure that I'm measuring is the oxygen and the water. So the key thing about this is if I'm collecting a gas over water, all right, that pressure that I measure is the water and the oxygen. So in order to get the pressure of the gas that I'm interested in, I have to take my atmospheric pressure and subtract the pressure of the water vapor. And so because this is done so commonly, there are tables that you can look it up and see, okay, if the temperature is this is what the water vapor pressure is going to be. Okay, so this will be this is either, it's going to be given in the problem, or when we do the lab for this, you would look it up on a table to find out, like based on what temperature you were doing the lab at, what the water vapor pressure would be. And so that's really kind of the only thing we do differently. If it's collected over water, whether we're using PIVNERT or the P1V1 over N1T1, the key thing there is you want to make sure that if it's collected over water, that the pressure they give you is going to be the total pressure. And in order to use it, you want to subtract the water vapor pressure from it. So like here, for example, it says collected by displacement of water, and it wants to know my grams. Let me make that a little bigger there. Okay. It wants to know my grams of magnesium, and I'm collecting it. It says I want to get 1.12 liters of hydrogen at a temperature of 26. So it's going to be 299, and a pressure of 748 torr. And so typically what I'll do is, as soon as I read displacement of water, I write next to that pressure that that is the total pressure. And so here it's giving me, where it says vapor pressure, that's the pressure of the water vapor that's present. So my pressure of my hydrogen then is going to be 748 minus, and we'll use 25.5 torr. So that gives me, let's see, 748 minus 25.5. So I get 722.5, and we have 760 torr is 1 atmosphere. So that gives me 0.951 atmospheres. Okay, so then I would use that to get my, to do my PIVNERT. So I have 0.951 times my volume. It's going to equal my moles of hydrogen, 0.0821 and 299. So N of hydrogen then is so I'm getting 0.0434 moles. And so then that would be the value, right? So it has, I made 0.0434. Separate that off there. And this is a 1-to-1. So 0.0434 would be the change there. And then magnesium is 24.3. So we do times 24.3. So getting 1.05 grams of magnesium is what I would need for that. Okay. All right. Okay, so let's look at another one here. All right, so I have potassium chlorate, right? Metal chlorates decompose into the metal chloride and oxygen. And so I think I'm going to need a 2, 2, and a 3 to balance that. And it wants the volume of oxygen, decomposing 5 grams. Let's see, temperature is 23 plus 273. So it's going to be 300. The pressure of my oxygen is, this is my total pressure, so 745 minus my water vapor pressure, which is 21 torr. So 745 minus 21, getting 724 torr. 760 to 1 atmosphere. So that's going to be 0.953. Okay, and so I've got all that information. So now this one, we're starting with my grams. All right, so that's potassium is 39 plus chlorine plus 3. So I'm getting 122.52 and 5 grams of that. 0.0408. So minus 0.0408. And this is going to be a 2 to 3. So the oxygen starts at 0. So plus, let's see, 0.0408. Going to divide by 2 and multiply by 3. So I get 0.0612. All right, and that's my moles. Okay, so my PivNert then, go down a little. So pressure 3, I'm solving for volume, 0.0612 moles. And my temperature was 300. So volume is 0.0612 times getting 1.58 liters on there. Okay, so that's one type of problem that involves the a mixture of gases. And so another one, all right, and this is a very handy expression to have, and I believe this is on the formula sheet for the AP exam. They have this. So the key thing is kind of just knowing how to use it. All right, and this, the font is not this exactly the same. You'll see for mole fraction, usually the X, it's more of a like sort of a curly Q X that they use for the mole fraction of a gas in there. And it's just essentially the fraction of moles of one specific gas. So it's the moles of that gas divided by the total. And so this is, again, like what we talked about before. So the partial pressure of a gas is going to be your total pressure times the fraction of the moles of that gas that are in the mixture. Okay, so looking at here it wants the total pressure that has a gram of hydrogen and a gram of helium in a 5-liter container, and it wants to know what are the partial pressures. So the first thing, let's figure out what our moles are. So 1, and we're just going to use round numbers here. All right, so 1 gram of hydrogen, that would be, so moles of hydrogen are approximately 1. And my moles of helium is going to be about 0.25 if we round off. All right. And so it wants our total pressure. So P total is equal to pressure of the hydrogen plus the pressure of the helium in there. Okay. So we can do 2 Pivnerts to get those partial pressures. All right, and we're going to kind of do this 2 ways just to show you that mole fraction expression there. All right, so pressure of the hydrogen times my volume is 5. My moles of hydrogen are 1.0821, and my temperature 273 plus 21. So I'm getting, what in the world? Let's try that again. Okay, 294. So my partial pressure of the hydrogen then is going to be 2 divided by 5. So I get 4.83 ATMs. And then I can do the same thing. Partial pressure of the helium is 5. So 0.25 moles of helium, 0.0821, and 294. So that is pressure of just the helium. So 0.25 times 0.0821 times 294. All right, 6.03 ATM. Okay, so I could get my total pressure just by adding 4.83 plus 6.03. Okay, so that's going to give me 10.86. Okay, or the other way, right, I could do it is that P total times my volume. And then if I do N total, so add the 2 moles, so I have 1.25 moles times 0.0821 and 294. So that gives me P total of, so 1.25 times 0.0821 times 294, and then divide by 5, and I get, wait, what did I just do? 1.25 times, did I make a mistake with my other? Oh, wait, I didn't divide that by 5. Okay, hang on. Let me redo that. Let's see, 0.25 times 0.0821 is 294 divided by 5. Yeah, there we go. That's better. Okay. Had to math error there. This should be 1.21. So let me go back up here, fix this. 1.21. So 4.83 plus 1.21. That gives me 6.04. There we go. Which is also what I get when I solve it that way. Okay, that makes more sense. And then now let's also to double check our that partial pressure thing, right? I could also get the partial pressures. So, right, just do the hydrogen. Partial pressure of hydrogen is going to equal the mole fraction, which is going to be 1 over 1.25 times my total pressure, which was 6.04. So if I do that, 1 divided by 1.25 times 6.04, and I get 4.83. So that's one thing is there's, especially with gases, there's usually multiple ways to attack a problem on there. So that was just kind of a demonstrating that part. All right, so here it wants the partial pressure of the carbon dioxide in a container, and it gives us the moles, and it's given us the total pressure. So for this one, definitely the easiest way is that the partial pressure of the CO2 is going to be the mole fraction of the CO2 times your total pressure. So partial pressure, so moles, I've got 5 moles of CO2 over my total is going to be, so in total, it's going to be 5 plus 3 plus 1, so 9. So 5 over 9, and it gives my total pressure is 1.05. So that's going to be 5 divided by 9 times 1.05. So 0.583 atmospheres is the partial pressure of the CO2. Okay. All right. So that's kind of an example of the different ways that calculations that you'll see with mixtures of gases in there. Okay, any questions? Let me stop sharing here. Go back to the Meet screen.
There's the one on the Jamboard, one more that I left.
Oh, okay. Let me go over. Okay, so what page on the Jamboard?
I think 10 or so. I don't remember, honestly. It's 9. It was the same one, but it said I got it wrong. So.
Oh, okay. Okay, so we're working on that one. And okay, so it said
50,000 for, because that's 5% of a million grams.
Okay. And then, all right, so we did 5%. All right, so 50,000, and the iron pyrite. Okay, so
I divided it by 119.975.
Okay, hang on. S2. Let me double check that on the molar mass of that one. Hang on. Because the problem has Fe S2. And in your, did you use FE2 S2?
Oh, I did use, that's a typo. I used I used S2.
Okay, all right.
That was a typo.
Okay, so let me double check that one. Hang on, let me go back to screen sharing. Wait. Okay, so I'm on the Jamboard here. All right, let me find, I just want to double check. So we're in this one. And 4. Okay. So this is problem number 4. All right. Oh. Okay, so 50,000, and they used, okay, what'd you say what molar mass were you using?
119.975.
Okay, okay, all right. So, all right, 50,000, that we're gonna divide by 119.
And you get the 416 that's in the table.
Okay, all right, so far I'm agreeing there.
Then
All right, and then it's a 2, right, so an 8 to 4.
Mm-hmm.
All right, so, okay, so times 2, give me that many grams, and then, so 32, 1 sulfur plus 2 oxygens, so 64.05 for your molar mass there.
Maybe that's where I messed up, because apparently, okay. Maybe that's it, because
Oh, yeah,
I
I
was
think
just
that's it.
slightly off somehow.
Okay. All right. Okay. Any other questions? The quiz is should be open. Let me go back and just double check the settings on it. Okay. So the quiz is open. It'll be open until 11 this evening. There is a 60-minute timing on it, so make sure you've got everything that you need for that. And there are, let me see, how many questions? 13 questions on it. 13 questions, and you have 60. I'm going to bump that up a little bit. Let's go another 20. Let's do 80 minutes on that. Oops. Changed the wrong thing there. Okay. Rate that. Oops. Okay. Now that's good. All right. Let's see. Let me go back. There's the Jamboard. Okay. Anybody else have any questions for me? Everybody know what? Yeah.
Is that timer until 11 p.m. or 11 a.m.?
It should be 11 p.m.
Okay, thank you.
Yeah. And let's see. And again, there is a quest for the stuff we did today, but I said it's not due until like a week from tomorrow. So that way, you can take a quiz and just sort of take a break from chemistry. Because I think the other one, let me go fix that. I'm going to fix that one too. Yeah, the gas stoichiometry. I'm going to move it to be the same day as the Daltons. It was due Monday, but I'm going to put it on Wednesday as well. Okay. There we go. All right. Okay. Any other questions? Okay, well, I'll kind of watch the Jamboard. If you have questions there are the two quests from the stuff we did last week. Those two are due this evening. And I think that's about all I have. Okay, so if there aren't any other questions, I will talk to you guys. Have a wonderful Thanksgiving, and I'll talk to you next week then.
Bye.
Bye.